introducing me. And once again, for those who are not here in my talk last time, I would like to thank the organizers for inviting me to give this series of lectures here. It's a great pleasure and honor for me to do this. Now, unfortunately, I am in the situation where I have to become today more technical. I thought that actually Makoto and the speakers before me will do this unpleasant task so that I will speak only about pleasant things. But before being able to tell you what is the content of this assertion of the Grothendieck's Anabelian geometry, I have to define at least very quickly what are fundamental groups of, I would say done right. Yeah, for algebraists, sorry, for algebraists. So this is just preparation. Et al. Fundamental groups. And it's very good that Grothendieck is not in the audience, because he would say, exactly like somebody said yesterday from that corner, this is completely wrong what we are doing. You don't do the things in the right way. But I do the things now in such a way that they relate to what we already know about fundamental groups from yesterday, but I do them in such a way that actually we have the definition also in characteristic P, and I mean in much more general. Okay, so what is the situation? So I will... So the situation will be the following. So X will be maybe an integral separated scheme, maybe of finite type, over something. Yeah? And this something is a ring maybe, or it's a nice ring, a Noetherian ring, or maybe a field. Yeah? Okay, now the first situation is, suppose that actually this something here over R. Now suppose that R equals is a field K contained in the complex numbers. Yeah? And maybe also to have less problems, I will say it's an integral normal or separated normal scheme. So here that is really important, and it's good that I did not say so normal. Yeah. Then I will first give a quick interpretation in two ways of what we learned yesterday, that are unramified or covers which are classified by the fundamental group of X. So what was yesterday? So yesterday we said we want to look at the following. So you have here X. So it was K of X here, and then you had K bar of X, and then here was Makoto's field Mx. Yeah? And what was this Mx? Well, these were functions which were algebraic over this field in such a way that they are multivalued and multivalued and defined everywhere multivalued but defined on everywhere on X of C, yeah, which are the complex points. And now, what is an interpretation of that? Well, interpretation of that is the following. If you just take a finite quotient of this, so I need a little bit more space here. Okay, so here once again R equals K subfield of the complex numbers. So, and then here is Mx. And now the point was that actually if you take Mx fixed under N should be an open subgroup in N finite index in pi 1 top of Xn. Yeah, then this is a finite extension here, and if you look at what happens in the topology, so now I have to erase again. So what is this guy? So this is now, so here you have X of complex numbers, And this is then really a true cover in topological sense, classified by this n as a subgroup of finite index. And how should I call this? Maybe x of c. This is maybe an x n of c. Yeah? That is a true topological cover. That means if you have a point here, then over this you have as many points as the degree. Maybe the degree here should be n. You have x1, xn points over every such point. And now we are at the place where we can understand what's going on from the algebraic point of view. Now, from this picture, we do the corresponding algebra here. And Makoto just said that by some theorems of somebody, you know that actually such a finite topological cover comes indeed from the algebra. And if you write down, then what this means is you have x here, well, x k bar, and then this you have xn, that is already over k bar, so. And from the algebraic point of view, this means that it is unramified. And I will define here very quickly. So fact, now I back here into the serious stuff. Yeah. Back to star. Now you do the following. So x is integral, therefore you can speak about x function field, yeah? And you can take some finite extension of this, let's call it k, and that sits inside the separable closure of this guy, yeah? So finite here. Now, at least something I expect from my audience, that everybody knows what is this. Well, yeah, that is the normalization of x in the field extension k of x goes into k. Yeah? And we say that now you take a point x here. Yeah, so x is a point in here, and you take the fiber of this, which I call x. So this is the fiber, yeah? Now, this fiber consists of finitely many points. And this is also what I expect from my audience, yeah? That if you have a finite and you have a normal, there's a normalization, the fiber is, well, that is.
What's the kappa of this?
This is the function field. Ah, okay. I have this k, and then I have to write for this maybe L. No, okay, so. Yeah. So this is a finite field extension, yeah? Okay. And I take the normalization, then over x I have the fiber, and I have finitely many points. And now the point is the following conditions are equivalent. So equivalences. So this is the finite and has degree maybe n. N is not good, then I have here an m. Yeah. Equivalence is the residue field, so k of xi over k of x, these are the residue fields at these points, are all finite separable. And one has sum of their degrees equals n. And second, only at one x, yeah, at one x. So the stalk of the differentials of this guy, so of xn over x, but here at x is not the stalk, this is the fiber, equals 0. Yeah?
I thought you assumed that x is normal, so why do you need to look at a normalization?
This is a normalization in a finite extension. Yeah. So now this is somehow elementary algebra, and hopefully everywhere one teaches this, so that this to find, and now if you come back here, when you look at everything over the complex numbers, and you think only about closed points, then this is then the complex numbers. These are all the complex numbers. Therefore, what does tell you this relation? This relation tells you that actually over every point over this point x in discussion, you have exactly n points. And it turns out that this is equivalent also to this. Yeah? And then now definition, say that, so this is x here. This was a large K over Kx is unramified if for all x in X, these two equivalent conditions are satisfied. I2 are satisfied. This is one. And second, then also say that xn over x is an finite étal cover. Yeah? Also say that xn over x is finite étal cover. Yeah. Now once again, the point is you check that actually being topological like before, topological cover, is equivalent to being from the algebraic point of view an étal cover. Or being equivalent to the fact that this field extension is not ramified. But, so we learn from the topologists, but now we are better. Because you can do this always. K can be everything. We know what is normal. We know this. Yeah? So this is very, very general. Okay. And now, so definition. But this is, as I said, if Grothendieck would be here and we would listen and say, this is the wrong definition. Actually, he could not stand also the other definitions he saw before. Okay. So let maybe, for now, yeah, so let be R a nice ring. So maybe, integral domain, nice domain. E.g. a field. And then you take X, some R variety. And then take R of X, maybe K of X like this. Yeah, so this kappa of X function field. So this is an integral, yeah. So in K, normal. Nice implies this, for instance, nice includes everything, yeah. So normal, integral R variety, and kappa of X maybe goes to, kappa of X viewed over K, where K is the quotient field of R, should be the function field of X over R. And then you consider the following. Let kappa X like this over kappa X be the maximal unramified extension of X, of K of X, kappa of X, sorry. Yeah, okay, so I should have said here now, the point is, if you have such a situation, and suppose that you take another finite extension, and suppose that X is also unramified in that, then it turns out that, if you take the fiber product of these two étal covers over X, that might be not integral, but if you take any connected component of the fiber product, it turns out that that is étal over X, and the function field of that corresponds to the compositum of these function fields in, say, in the separable algebraic closure. Okay. Now you take this, the maximal unramified extension of K of X in, say, I say here, in some fixed algebraic closure K of x bar. Yeah. Then it turns out that this, by what I said before, over kappa of x is a Galois extension. Is a Galois extension. And set pi 1 of x equals Galois group of this large K of x over K of x, kappa of x. And call it a fundamental group set and call it the fundamental group of x. Now, obvious remark. Naturally, in this, I just the separable closure of kappa, so this over K is contained, embedded in a canonical way in this. Yeah? With such an embedding, maybe without K here then, like this. Now the separable closure embeds into this. So you see that actually this criterion, you see immediately this criterion is satisfied. Yeah? For this. And in particular, thus canonical exact sequence how should I say, maybe? Okay, so and this embeds, it's fine. Yeah. I have here pi 1 of x, and this pi 1 may be et al. Yeah, so this is, sorry, so this is, yeah, so you have pi 1 of x et al. Of canonical way gk. So, and since I said geometrically, did I say geometrically? I did not say. Maybe this is not nice domain normal geometrically integral. Yeah. So geometrically integral K variety. So then this is subjective because geometrically integral means more or less that K, the function, this is algebraically very close into this. And now you have here a kernel here, which I will alge. And you see, maybe it's good that actually Makoto did not do all these things because he had different notations. Now, he defined, for him, everything here was geometric. Fine. But, so what is this? Well, this is that what, in this picture, so here, the Galois group that we've seen a couple of times, this is GK. And then here, you have something which was P1, well, here, this is P1 alg of x bar. That means of the base change of x, well, x viewed as variety over the algebraic closure of K. And this is exactly this part here. Pardon? That's, again, a bad notation.
Why are you calling it alg here and pi 1 et al?
So you say...
Why not just call it h bar and use the same pi 1 algebra et al?
You... Now, since you are one of the organizers, I cannot contradict. It's okay, so it's good. And then naturally, so language, then pi 1 et al. Of x bar is also called pi 1 alg. Yeah. Now, maybe examples. So, well, suppose that X is really a field, yeah? So X equals spec of K, yeah? So simply K some field. Then you see what is pi 1 of X. So pi 1 of étal of X is simply, well, you take all possible field extensions such that actually the residue fields are separable. What does it mean? There is only one point, there is only one point, simply the field extension must be separable. So you see that this is more or less GK. And now suppose that, maybe here, so this is example.
Are you assuming that R is equal to a field when you write down the exact sequence?
That's a very good question. Maybe, yeah. These people, yeah. Thank you. So that's very good. So I view everything over K there, yeah. But why I put that with R there is, yeah, this is clear now, yeah. So I view the variety over K, not over R, and then you have this exact sequence. And maybe some other examples, yeah. Suppose that that X is really a DVR, yeah. So equals R, not. So now I'm sorry, it's a DVR. What is this? Is a spec of, spec of R, and R is a DVR. Yeah, so then what is pi 1 of X? Well, pi 1 of X is then, I should now ask my students, can somebody help me? So this is GK unramified. Yeah. So this is the maximal Galois extension, unramified extension of the function field, and so on. Now, what tell us the topologists? So, using topological input, we have the following situation. R is now K, contained in the complex numbers. Then we already know, so you see by the translation, then P1 alg of X is of xk. Now it's equals to k. So this is simply P1 top xn completed. Yeah. Exactly, this is what we learned the last time. And once again, just checked actually that these conditions in the topological case are equivalent to the fact that this is a true topological cover. Yeah. And therefore, we know interesting things about this. Yeah, say X is a GR curve. Id est. So now I'm going to define what is a GR curve over K. So this is means id est. X is a normal. Well, more normal means the same as regular, or same as smoothing characteristic 0 for curves. Yeah, curve, and say let be x tilde regular completion or normal. I said okay, so normal completion of x, and then I denote by s the complement. And I say x bar is as usual, so it's x k bar, and then x tilde k bar is like usual. Yeah. And then s bar is simply s k bar. So then this is x1 xr. Yeah. And the genus, so G equals genus of x tilde. Yeah, so this is a GR curve. So a GR curve is by definition a curve, now in very general, a curve which has a smooth completion such that when you view everything over the algebraic closure, then the complement of, well, the complement of the curve x in the smooth completion has cardinality R, and the genus of the completion is G. Yeah. Then what tells us the topology? So by topology plus complex analysis set PGR by definition. So this is the group generated by A1, B1, AG, BG, and C1, CR, with the famous relation product of the commutators times product of the CJ equals 1. Yeah, and what is this? Well, this is actually, in a canonical way, this is pi 1 top of x un. Yeah. Then what is pi 1 alg of x? Well, this is simply the profinite completion of GR. And here it's a very big hail on the topologists. The algebraists are nuts. We have not a slightest clue how to prove this theorem by algebraic methods. If somebody can do this, please, I would like a lot to be the second person hearing how it goes, because he must be the first one. Yeah? So, no algebraic proof, yeah? No algebraic proof. Say yet. Maybe by the end of this conference. And by the way, so Grothendieck-Mensen makes a very interesting comment about this in SGA1. He says, naturally he complains that actually we have no idea how to do this, and he says that actually it must be very extrêmement intéressant to find an algebraic proof of this. So maybe, pardon?
About for genus 0, even then?
Okay, now further comments. If you want to become famous, you just have to do it for any genus bigger than 1 and R equals 0. Okay, maybe here. Very good, thank you. So, maybe a further definition here. Definition concerning this, a GR curve is called hyperbolic if 2g, should I write it like usual? So minus 2g plus 2 minus r is less than 0. And actually, the answer to your question is we don't know to do this for any hyperbolic curve. And the second answer to your question is, if you know how to do it for a single hyperbolic curve, we know everything.
Yeah.
So
you can't even do it for an elliptic curve minus the point?
Dick, tell me how to do it. Yeah, elliptic curve minus 1 point would be perfect.
You shouldn't have made those nasty remarks about topologists.
But why? It's not nasty. It's really, it's amazing that
You're saying we can't do it for P1 minus 3 points.
we can't do it for P1. It's only, look, it's so bad we don't even know that, I think we don't know that P1, with algebraic methods, we can't prove that actually the finite group of P1 minus 3 points is finitely generated, topologically finitely generated. It's so bad, yeah? And we also cannot prove that it's a finite quotient of something with, so there is no way actually to prove the true theorem. By the way, so maybe a remark here. There is a nice interpretation. So the algebraists don't have an interpretation for the AIBI, so maybe I don't know what. They don't have an interpretation. But CIs have an interpretation, namely these are inertia elements, so interpretation. Okay, so I don't want to annoy topologists, although it's amazing. You say something nice about topologists and then you are criticized. So remark, CI have the algebraic interpretation of being inertia, some very special inertia elements over the points x pi. Okay, now
We can plug the extension provides the A's, I's, and the I's are given by the vector by Gaussian in the report.
yeah,
So we know how to do that algebraically.
I think that is for me not an explanation. The true explanation is that of the topologist. I mean,
Sorry, what about the pro-P complexities?
say
Well,
no. No, we don't know this. Maybe no meta-abelian.
wait, I mean, related
For
to
P1
that.
minus 3 points, for the pro-P completion, we must be able to do it, no?
Well,
No.
we can do it with a pro-unipotent.
That's a joke. From some point of view, sorry, no, I mean from some point of view. From this point of view, it's very far from saying something essential. Yeah?
The point I was trying to make with the Abelian cover is that what we have to prove there, what we know how to show that the algebraic analytic is at least as good as that. What
Yes.
we cannot prove is that there's nothing else.
Okay, you are right, yeah. But what I understood first is that you said that we have an interpretation of IA, IBI. I mean, it's not
Well,
that.
I mean, it's,
Okay.
you can construct the cover.
Yeah. So the abelian stuff follows indeed with Jacobians and generalized Jacobians, yeah. But it's only the abelian stuff. I understand what you say, and therefore there are at least as many generators, yeah. Okay. Yeah. So the big problem is, as I said, we are not able to prove, for instance, that it's finitely generated. Yeah. And have absolutely no clue that actually look what the topologists tell us. You can find very special generators of the inertia whose product is 1 and generate the whole group. This is really... Okay. Now I want a little refinement of this. So maybe the same fundamental group. Maybe those who take notes, please don't write down comments which could annoy somebody. Yeah, so the same fundamental group. Okay, now the situation is as follows. I will now say K is some base field. And then I will take now really x0 over K. So this is a regular complete K variety. For instance, now, so if this has positive characteristic, then we know maybe that such things are not, maybe seldom, yeah. We do not know how to desinglorize, particularly given a function field, we do not know whether we have always regular complete models, but we hope it is like that. And now you take maybe P1, PR, finitely many, well, it's clear that it's finitely many Weil prime divisors on x0, and you write x equals x minus union of the PIs. Yeah, and now I take, so we know already, so we know what is, so x over x dashed, maybe, some finite et al. So these are Weil prime divisors, and this is x0 means, thank you, yeah. So I take the complement of these finitely many, but I would say distinct, yeah, so that, fine. And now I take here finite et al. Cover. And then if I take now, maybe let's say Vi should be the valuation on k of x defined by Ox Pi. So this is the local ring, well, xi, where xi generic point of Pi. Now since we are regular, more than normal, these are discrete valuation rings, and then you have these discrete valuations, and then you can ask yourself, okay, so if I take some finite et al., maybe Galois cover, yes, finite et al. Galois. I write too small, so finite et al. Galois. Yeah. Then if you take one of these valuations, maybe V, then this has finitely many prolongations. Okay, so look at the corresponding field extension. So, how should I do it? I stay geometrical, so I have to choose a language. So then, if you have such a point xi here, maybe x, over this you have the fiber xx, and this consists of finitely many j dashed, so 1 and so on, xr points. So over this point, yeah? So all these lie over that. And then you can ask yourself, okay, so what is the behavior, the local behavior at the corresponding DVRs, yeah? So you have here Oxx, and over this, for every chosen point, here you have Ox dashed xj dashed. So this is an extension of DVRs, discrete valuation rings, and I will not tell you, so you have the fundamental equality holds and so on, and then for this, so finite extension of DVRs, discrete valuation rings, yeah, and in particular, then you have the E of xj dashed over x. Okay, so also the f of xj dashed over maybe the finite ring extension, so finite field extension, a residual extension. Now definition, x dashed to x is called tame, tamely, or tame at xj, at one of these xj dashed. If, as usual, that is an extension of tame extension, that means if characteristic of k does not divide E of xj dashed over x, and this is separable, yeah? So k xj dashed over k of x separable. And as before, the composition of two tame extension is again a tame extension, and so on, kappa, and then finally, so this is one, and second, 2 P1 tame of x should denote, so denote the factor of P1 of x, which classifies, parameterizes maybe, yeah, so parameterizes all finite tame et al. Covers of x, yeah. And so by definition, so remarks, first, one, as before, so exact sequence, so there exists a canonical exact sequence. 1 goes to pi 1 tame of x bar, goes to Now I have a problem. Pi 1, so that's correct in this case. Goes to 1. So here again, regular complete, and here geometrically integral. Yeah, so then you have such a canonical exact sequence, which follows from the other sequence before. Yeah. Okay. Now I have.
So your notation does not depend on x. So does it depend? I mean, independent of Charles computation.
That's a very good question. Now the point is, you say this does not depend on x0. Yeah. The point is that actually it does indeed not depend on x0. But you have to, so the point, in general, if the variety is complete, then the fundamental group of a complete regular variety is a birational invariant of the variety. And, well, I have to say maybe also other things, yeah. So the point is that if you have a ramified cover of a regular scheme, then the ramification locus is always pure of codimension 1. Yeah, so this is the theorem about the purity of the ramification locus. And how do you see that? Well, it was here, but it is gone. So actually, where is the ramification? There where the modulo of differentials does not disappear. But now you maybe know that actually the annihilator of the modulo of the differentials is the different. And then that is on a regular variety. The local rings are all factorial. And that means that this different locally is generated by an element. And therefore the support of the different has pure codimension 1. That's a good question. And now here, so you would have to do something, yeah, a little bit of work here. If you take another regular model, then these two regular models have the same fundamental group, and then you see that actually. Okay. We will anyhow speak only, I did this just in order not to appear that's a big mystery or something like this. We will use it only for curves. Okay. So for curves, now one knows the following. In characteristic 0, thanks to the input from topology and complex analysis, we know more or less everything. So there is no difference between tame and fundamental, the usual fundamental group, because in characteristic 0 there is there are no pure inseparable covers. But in characteristic P the things are different, and here is what is known. So okay, so facts maybe. So 1 or maybe 0. If characteristic of K, now I switch from large K to little k, 0, then pi 1 equals pi 1 tame. Yeah, so there are no differences between these. Nevertheless, in positive characteristic, now if characteristic of K equals P positive, then so then there are a couple of things one has. First, theorem by Shafarevich, which says the following. I will speak only about curves. So let X be a GR curve. Yeah. In higher dimensions, there are problems with what is known, what is not known. So let X be a GR curve, then you have this, and now what happens in characteristic P? Well, the theorem of Shafarevich says that actually at least this guy, P1, P of X, 0. So curve X0, it's smooth completion, yeah. Okay. Then Shafarevich tells us the following. So A. P1, 0. That means, and what is this? Now, so I would have to say here again. Now I realize how good the idea of numeral. So, yeah, that should be. Now I have to check everywhere. I don't. I think I'm done. Well, one can use this notation. Perfect. So, and I will not write et al. Anymore because it's always et al. Yeah? So now the point is that the theorem of Shafarevich tells us that this guy is a pro-P free on Rx0 generators, where this guy is the so-called Hasse-Witt invariant, yeah? So Rx equals Hasse-Witt invariant of x 0. Well, I can write 0, yeah. And what is the Hasse? There are many descriptions of this guy, also with differentials and so on and so forth, but one easy is you take the Jacobian of x0 and you look at the torsion, the p torsion of this, that is a vector, fp vector space, and that has a dimension, and that is Rx, that is by definition this guy in particular, yeah, and so take here effect. This Rx is anything between G and 0, but not more than G. Yeah? Now what happens if R is positive? Yeah? If R positive, then pi 1p of x bar is a free pro-P free group, pro-P free, on many generators, on K-bar generators. Yeah, okay. Pardon? I said, so this is the maximal, so this guy is the maximal pro-P quotient, yeah? This guy, maximal pro-P quotient of P1 x bar. Yeah. Okay. What happens now on the prime to P part, away from P? So that is famous theorem by Grothendieck called the specialization, well, which is a special case of the specialization theorem by Grothendieck. And it says the following. So now the next big fact is, do I have to stop now or what? In 10 minutes? Maybe, so, yeah, 5 minutes. So I just write the, no, yeah. So this is specialization theorem of Grothendieck. Yeah. So it says the following. So A, there exists a surjective homomorphism. Maybe special, it's not bad. So PG goes into pi 1 of x0 bar. In particular, this guy is finitely generated, but we have, that's it, what we, so also most 2G generators. Yeah, and maybe x0, yeah, so, and px0 induces an isomorphism on the maximal prime to P quotients. Where this, I think we've seen already in Makoto's talk, you can complete this discrete group with respect to many families of finite subgroups. And here is the completion with respect to all finite quotients of order prime to P. Yeah? And then this is isomorphic to pi 1, again, prime then of x0. Yeah? And second B, what about the open curve? Okay, so there exists a canonical, not surjective again. If you make some choices after that everything is canonical, homomorphism, PGR goes into pi 1 tame of x bar, which induces an isomorphism PGR prime goes to P tame prime. Let's not exaggerate. Maybe P prime T of x bar. So what do I say? So then this tame is gone, yeah? That's again. Yeah, okay. That means this gives you a relatively good picture of what is going on. Well, really very relatively good. So these are finitely generated groups. They are quotients of such finitely groups. And we know the structure of these guys only by topology and complex analysis. But this gives you, will tell you something about this. We know precisely what is the quotient at the prime to P quotient. That means we'll call it the prime to P completion, finite completion. And in particular, now from this, so you have here 1 goes into pi 1 something x bar, goes into pi 1 something x, goes into gk, goes into 1. You have something here of arithmetical nature, and you have something here of geometrical nature, which you know or do not know very well. And anyhow, you have a representation of this group on this as a group of outer automorphisms of this group. And the question is now, the theme around in the Anabelian geometry is, okay, what does, say, the interaction between this and this? In the case this carries a lot of information, that means the curve is hyperbolic, and this carries a lot of information. For instance, it's finitely generated. And more or less the question is, then this, the interaction can see everything about the curve. That means you can recover the isomorphic type of the curve from this interaction. And I will speak then next time, tomorrow, about.
You have pi 1t also?
So here, this can be anything, yeah? So, pardon? Yes.
Part A of it. So we are already in the middle of the question now,
Yeah, this I understand. So please, what is?